To really understand Gauss' law, we have to know certain key concepts. The concept of electric flux, electric field lines, and area vector. Let's start with electric field lines. So what do we actually mean by electric field lines? The concept of electric field lines was introduced as a way to visualize the electric fields. Let's take a kind of chamber which has certain electric field inside it. We don't know the direction of electric field, so let's take a test charge Q and place it inside this chamber. We know that force applied on a charge in the electric field is charge times the strength of electric field. So inside this chamber, the charge will experience a kind of force in the direction of electric field and it will start moving. By the movement of this charge, we can determine what the pattern of electric field lines is in this particular chamber. This trajectory drawn by the charge is electric field line. Now there are some properties of electric field lines. The electric field lines are continuous smooth curves without any breaks. So this can be an electric field, this can be an electric field. Electric field lines never intersect each other, so this cannot represent electric field lines. There is also one kind of nature's fact about electric field lines, that they start at the positive charge and end at the negative charge. They cannot form a closed loops. Now let's get to the concept of area vector. If you were given a task to define a certain kind of direction to the area, how would you do that? Would you make area vector parallel to the plane of area? But that would be ambiguous choice, as the area vector in the plane would have many directions and doesn't really define a unique direction for an area. But can we make the area vector point at perpendicular direction? This seems more logical than the previous choice, because this kinds of defines a unique direction to the area. So area vector is defined in a direction normal to the plane. The magnitude of area vector is of course the actual area of the sample. It's just the direction which gives rise to the concept of area vector. Now let's move on to the concept of electric flux. When you think of flux, think of kind of flow. A flow of liquid through an area can be said as a flux of liquid through a certain area. Let's consider this arrow shooting machine. This machine shoots out multiple arrows in every direction. Let's take a kind of sample area. So what happens when we tell the machine to go shoot? There is a definite amount of arrows passing through this sample area. This is what is flux. So we say that the flux of arrow through the area is the number of arrows passing through this area. Here the flux of arrow is 3. Similarly is the concept of flux of electric field. In electric field, the flux is defined as number of electric field lines passing through a certain area. I will give you an intuitive approach to the definition of electric flux. Let's set up a random electric field and select a certain sample area. Now the electric fields are passing through this area. So obviously there is a flux, because earlier I defined flux as number of electric field lines passing through the area. Now what happens if we increase the electric field lines? Well, obviously the flux increases because number of lines passing through the area increases. What happens if we increase the area itself? Now the area can accommodate more electric field lines. So again the number of electric field lines passing through this area increases, so flux also increases. Now what happens if we tilt the area by a certain angle theta? As you can see, the flux decreases because less amount of electric field lines are now passing through this area. From all these arguments, we can confer that flux is directly proportional to the electric field, to the area, and some term of theta, such that when theta is equal to 0, the flux is maximum, and when theta is equal to 90 degree, the flux is minimum. Here theta is the angle between the electric field vector and the area vector. This condition is fulfilled by a mathematical term cos theta, and this is precisely what the formula for flux is. Phi equal to Ea cos theta. We can write it in a more fancy mathematical way using dot products. Dot product of electric field vector and area vector. Now let's move on to the concept of flux through closed surface. The thing about closed surface is that area vector always changes its direction at every point on the closed surface. So how do we calculate the flux through closed surface when everything is varying? Well, one way to do is we divide the closed surface into very small infinitesimal surfaces and calculate the flux through these surfaces and sum them up. So the flux through small area, which we call as dA, is E vector dot dA vector, which is the definition of flux as defined earlier. So what is the flux through whole area? We sum all the fluxes through small area. We can write it in a more mathematically apt way. We can write flux as the integration of all the flux through small areas. Now integration is a mathematical way of saying that we are summing over very small areas. The circle I drew in the integration sign signifies that the integration is performed on a closed surface. Finally, we are ready to tackle with Gauss law. Consider this special case of a closed spherical surface. But what is the flux through this surface? It's zero because I don't see any electric field lines passing through this surface. So what happens if I bring a unit positive charge and put it inside this closed surface? So the flux does increase because there is now a definite amount of electric field passing through the closed surface. So what happens if I bring another unit positive charge and put it inside this closed surface? The electric field lines again increase. Now this simple argument tells me that flux is directly proportional to the charge enclosed inside this surface. And this is precisely what Gauss law is. Flux is equal to charge enclosed upon epsilon naught. Epsilon naught is a constant. The spherical surface here is called as Gaussian surface. These Gaussian surfaces are imaginary and this Gauss law is just a tool to actually find out the electric field at a certain point. Now let's use this tool of Gauss law to find the electric field due to an infinitely long line of charge. The electric field due to positive charge, as we saw earlier, radiates outwards, which means that in an infinite line of charge the electric field is pointed radially outwards. We are given a charge density lambda. Now this is nothing but the charge per unit length. That is, if we take a unit section of this line, the amount of charge in that unit section is lambda. Now let's kind of draw a Gaussian surface. A cylindrical Gaussian surface would be apt here because of its symmetry to this line of charge. You can draw any other Gaussian surface if you like, but calculations are going to be much harder in other random Gaussian surfaces. So let's just stick with cylindrical Gaussian surface of length L. Now let's write down the Gauss law at top of the page. The left hand side of the equation is what we know as flux. Now we have to calculate the flux through the Gaussian surface that we made. The flux in this case is due to the curved surface of this cylinder and the flat circles at the side of the cylinder. Now let's calculate the flux through the curved surface. If we take a segment of area on this Gaussian surface, we see that area vector and the electric field vectors point in the same direction, which means the angle between them is equal to 0. Hence theta is equal to 0, which again implies that cos theta is equal to 1. So the flux in this case becomes closed integral of E and dA. We can pull E out of this integration as E is constant throughout this Gaussian surface. That's why we chose this Gaussian surface. If we had chosen a different irregular Gaussian surface, E would vary and it would make this integral a lot harder. The closed integral of small segments of curved surface is nothing but the curved surface area of the cylinder, which is 2 pi RL. So the left hand side of the equation becomes E into 2 pi RL. On the flat sides of the cylinder, the angle between the area vector and the electric field vector is 90 degrees. Cos of 90 is 0. So the flux through the flat sides will be 0. So the left hand side of the equation becomes E into 2 pi RL. Let's solve the right hand side of this equation. Now the charge enclosed would be nothing but charge density into the length we are considering. Here we are considering the length of Gaussian surface, which is L. So the charge enclosed will be lambda into L. So the right hand side of the equation becomes lambda L upon epsilon naught. Let's put this thing together and see what electric field we get. L cancels out from both sides, and obviously it should, because L is our imaginary surface. Electric field at a point shouldn't depend on some imaginary thing that we considered. So the electric field at a distance from this line of charge is lambda upon 2 pi r epsilon naught. The r obviously is the distance of line of charge from the point of consideration.